Hi, Professor.
I don't see you guys anymore. I'm connected to my iPad. I don't think you see me either. So
No, I don't.
But you see my screen, so that's
Yes.
what you need. So
yes, very well.
Okay.
Okay, so let me. Okay, it's already 3, so let me get started. Welcome everyone to our third seminar on optimization and real algebraic geometry. We are pleased to have Antonio Lerario from CISA, which stands for the International School for Advanced Studies at Italy. So Antonio is going to talk about Zonoid algebra. Thank you.
Okay, yes, thanks for the introduction and thanks for the invitation. I feel a little bit at home giving this seminar. So the topic of today, it's I would say a little bit unusual. It might sound exotic for some people, but I'll try to justify it at least how I got interested in this topic historically, and I hope to get also your interest. So essentially, what I want to do today, I'm still on the first slide, don't worry, is to explain that on a special class of convex bodies, which are called zonoids, and I will tell you in a second what they are, there exists a ring structure. And this ring structure mimics, it is a way to interpret geometric operations, averaging operations in homogeneous spaces. In the same way as the cohomology ring is used in algebraic geometry to describe intersection theory. Okay, so this is my main motivation. I will explain this, okay? So let me really start with the simplest example, just to give a feeling, okay? Just to give a feeling. So let's start with the classical picture over the complex numbers. See, I pick hypersurfaces in complex projective space, each hypersurface of degree, okay, d1, dn, so n hypersurfaces in complex projective space of dimension n. And I assume they are in general position, so I use this sentence, generic hypersurface, okay? So this means for the generic choice of hypersurfaces in the space of hypersurfaces, what I'm going to say, it's true. And what is it true? It is that the number of points of intersections is the product of the degrees. Of course, I think everyone is very familiar with this fact from classical algebraic geometry. You take n equations of degree d1, dn, number of solutions is the product of the degrees. And in fact, you don't even need essentially like this genericity assumption if you allow to interpret how to count non-transversal intersections. But okay, so what is the interesting thing about this identity? It is that it can be formulated, it is an identity which is formulated in a ring. It is an identity formulated in the cohomology ring of the complex projective space. So essentially, you use a little bit of Poincare duality, cup product, and the intersection product, and you transform essentially the cycle associated to the intersection of these hypersurfaces into a multiple of a point, and now to compute this multiple, you use a cup product rule. So you use the fact that the intersection ring in the Grassmannian is Poincare dual, in the projective space is Poincare dual to the cohomology ring, and you can compute this d1, dn using the definition of degrees. For instance, that it's the number of points of intersection with the generic hypersurface, which means testing with the generator of the cohomology ring. Okay, so there is a ring describing this intersection theory over the complex numbers. Very classical. Now let me switch to something a little bit more exotic. I don't really want to go into random algebraic geometry. I just want to give you an intuition of something that attracted my curiosity at some point. So now instead of picking, but now we pass to the reals, okay? And instead of picking generic hypersurfaces, now I pick random hypersurfaces, which means, if you want, that they are no longer defined by generic polynomials, but I put some probability distribution on the space of real polynomials, And now I integrate with respect to this probability distribution the number of points of intersections. Okay, so you can imagine that you sort of like tossing an hypersurface. Okay, you get n many hypersurfaces displaced at random in projective space, and you ask for what is the expectation of the number of points of intersection. And that's a pretty nice and classical, I would say nowadays classical from the 90s, theory developed by Mike Shub and Steve Smale, and gives the fact that like this expectation of the number of points of intersection, it is the square root of the product of the degrees. Okay, very nice statement, I think, but in some sense a little bit unsatisfactory. So we are doing some intersection here. Okay, we are averaging. Okay, and we get this square root of the degrees. It's not clear if this operation of averaging an intersection has some cohomological meaning. And in fact, maybe, as I just said, cohomological meaning, it cannot have it because things in cohomology are invariant under deformations, and real hypersurface, you can deform them and even make them not intersect. Okay, so it seems no.
Antonio, can I ask a question?
Yes.
I see that there in the footnote there's some explanation of what you mean by random, but
Yes.
but I'm not. I'm sure there's a more precise explanation. What
I will say.
What sort of randomness?
Yes. Let me say precisely. I don't know. Laszlo, is it you asking this question? I don't see. Okay. So pick the space of complex polynomials. Okay. Now choose. I don't know if you are familiar with the Bombieri-Weil scalar product Hermitian structure on the space of complex polynomials, but I'll say in a second, maybe. Just maybe the best way. Okay, maybe the best way and the simplest way is this. Let me zoom a little bit. I pick a polynomial p. Okay, x as a combination of Gaussian combination of Gaussian combination of scaled monomials. Okay? The psi alpha are mean 0 variance 1 Gaussian. Okay? This is essentially the same as picking the some Hermitian structure on the space of polynomials, passing it using Fubini study to the space of complex polynomials, inducing the space of complex polynomials with an Hermitian metric, restricting this to the space of real polynomials, treating this as a probability space, so it's a projective space with some measure, and sampling polynomials from this measure. Okay, this is the construction. It is very closely and very much related to an Hermitian structure on the space of complex polynomials. Okay, in this sense, this is why I'm taking this to the 1/2, by the way. Okay, I don't know. I hope this answers the question. But the main point for me in this formula, thanks for asking, it is not really that here I get the square root of the degree, which I think it's fascinating, but rather than this formula, it is in some sense multiplicative in the degrees. Okay, of course, there is a square root, but this fact that it is multiplicative in some sense suggests that maybe there is a ring structure underlying this type of operation. It's not a cohomology ring, it cannot be, but maybe there is something. Okay, this was a first piece of motivation. Now I'll give you another example, which maybe convinces a little bit more that there is a ring, and then I will explain, of course, this ring is this ring of convex bodies. Here is another example, again from algebraic geometry. So classical question, pick 4 lines in complex projective space and assume that these 4 lines are in general position. Now question, how many lines intersect all these 4 lines at the same time? So if you just pick 2 lines, there is infinitely many. If you pick 3 lines, there is infinitely many. If you pick 50 lines, there is no lines intersecting all of them. There is a threshold here. If you pick 4 lines, there is finitely many. And of course, these numbers are not just thrown at random. The reason is that the set of lines eating a line, it is a codimension 1 submanifold of the Grassmannian of lines, subvariety of the Grassmannian of lines. The Grassmannian of lines has dimension 4, so I'm putting 4 conditions on a 4-dimensional space, a 4-dimensional manifold. That's why I get, I expect to see finitely many points. Okay, answer to this question over the complex number, there is precisely 2 lines eating generic lines, 4 generic lines in CP3. How do you compute this number 2? You compute in a similar way as you do this computation here for the complex number. Now, in the case of when you work with the Grassmannian of lines, computations in the cohomology ring of the Grassmannian are just called Schubert calculus. That's the name to if you want, performing computation in the cohomology ring of the Grassmannian. Okay, so using Schubert calculus, you can compute that there is precisely 2 lines eating 4 generic lines in CP3. And of course, you can ask all sort of questions of this type. So how many k-dimensional spaces intersect at some dimensional space of dimension 4 in 3 dimensions, something in this dimension, and all these type of questions, they go under the name of Schubert problems. So very nice. So now let me ask the same question now over the reals, but replacing the word generic with the word random. So now there is, in fact, a unique, meaningful probability distribution on the space of lines, which is just the uniform distribution on the Grassmannian of lines. Okay, so pick 4 lines uniformly distributed on the Grassmannian, and now ask for the expectation of the number of lines eating these 4 lines. Okay, in some sense, it is the random version of this question. By the way, before going to random, there is no generic answer over the reals. There are configurations of these 4 lines which have no real lines intersecting all of them, and there are configurations of these 4 lines for which all the complex lines are also real lines, so defined over the reals. So this makes sense. In the space of configuration of 4 tuple of lines, there are 2 open sets, big open sets, one on which you get 0 lines intersecting all of them, and one on which you get 2 lines intersecting all of them. And these open sets are separated by some sort of discriminant, which as usually happens in real algebraic geometry. It has real codimension too, so it can separate the space. Okay, let's go back to the random question. So essentially you are charging each of these open sets with some measure, and you are integrating on these open sets the function number of solutions. And you ask for the expectation of the number of real lines, and it turns out that this number, it is the volume of a convex body. It's a convex body which leaves, it is more or less can be interpreted as a tensor product of balls. I will explain maybe later what is the tensor product of 2 convex bodies. And these balls live in the tangent space to the Grassmannian at one point. Tangent space to the Grassmannian, it's a space of endomorphisms. So it's an R2 tensor R2, so endomorphisms from the space to its orthogonal complement, for instance. So it's a convex body inside this space. And this convex body, it is one of these special convex bodies, which we will meet in a few minutes, which are called zonoids. What does this have to do with the previous slide? So where is the suggestion there might be some ring behind this type of computations? Well, the volume of a convex body, it is, in some sense, it is the polarization of a multilinear map on convex bodies. The multilinear map being mixed volume. So if you scale convex body by a multiple, you would get that the volume scales by the multiple, in this case to the power 4, which is a dimension in which of the space in which the convex body of the convex body. So there is some multilinearity in the same way as computation in a ring are multilinears, because it's a ring. So in the product you can take off multiples, and there is again some multilinearity here happening. And okay, so this is a suggestion that there might be a ring where this identity here and this identity, and in fact even this identity, can be formulated. Okay, so let me now change it. So this is a more or less a motivation for me, okay? Searching for this ring and trying to explain what's happening. Okay, so convex geometry. Let me tell you a little bit. I want to introduce this special class of convex bodies on which I'm interested in. So I pick V, real vector space, and I call K of V the set of convex bodies in V. So let me recall, these are compact convex subsets in V, okay? So if I take two convex bodies in V and I take two positive real number, I can first of all scale a convex body by a real number. So I take just a dilation if you want. But then more interestingly, I can also add two convex bodies. And this addition is called Minkowski sum. And how it is defined, it is a new convex body, which consists of all points, 1 point in here, plus 1 point in here. Okay, you have addition in the vector space, and now you take the set of this is classical addition of subsets. What turns out to be, in the case where the two subsets are convex sets, is that this is still a convex set. Okay, it's Minkowski addition. So in this way, the set of convex bodies, it is a cone. You can scale by a multiple, and you can take addition. But more in yes.
The bodies are supposed to contain the origin, or
okay, so it's not supposed in general, but thanks for asking, Shogata. For the sequel of this talk, I think it would be simpler for the audience to think that these convex bodies are centrally symmetric, but it's not needed. But I was going to say this in a second. For practical reasons, maybe whatever I'm going to say later at some point, it's going to be true for centrally symmetric convex bodies. Otherwise, there is some little adjust that should be done in the statements of what I'm going to say, because one needs to take care of the center of these convex bodies, which in some sense in our zonoid ring, it's just a direct sum with the vector space itself. But I will get to this in a few slides maybe. Okay, but in this slide, no, they're not supposed to, even if it's more practical for us to think that, yes. Something interesting about the space of convex bodies, it is that it's also a metric space. So if you fix a reference body, in this case, I chose to fix the ball, the unit ball, with respect to some scalar product. You can turn this space into metric space in this way. You define the distance between two convex bodies in this way. You take the infimum over the positive epsilon of, you try to fit the first convex body in an epsilon neighborhood of the second, and the second in an epsilon neighborhood of the first. And the smallest epsilon for which this works is the distance between the two convex bodies. Okay, it's called the Hausdorff distance, and this distance turns the set of convex bodies into a complete metric space. Okay, so very infinite dimensional. It is in fact homeomorphic to a cone inside the space of continuous functions on the sphere if you work with support functions. But if you're not familiar with this, just ignore it. So there is a way to turn this set of convex bodies into a metric space. So what are zonoids? So, and I apologize for this. I don't know, just my English, it's getting a little bit rusty, if it's appropriate to say what the hell are zonoids. Some native speakers told me yes, but I don't know. Maybe it's a little bit less, I mean, too much not formal, so I don't know. So
what on earth?
Well, yeah, I will change it a little bit. Let me put these, okay? I feel more comfortable now. I asked to someone, but what are zonoids? I like it this a little bit more. Okay, so what are zonoids? These convex bodies I want to say something about. First of all, let me tell what are zonotopes. So you see, there is a special class of convex bodies which are segments. These are convex bodies, very, very teeny, very tiny, very thin. And if you take addition, Minkowski addition of segments, like in this picture, you get what it's called a zonotope. So a zonotope is a Minkowski addition of segments. Okay, it's pretty much this. And now you see this, it's quite nice. and in some sense, the set, it looks, how to say, quite clear, right? That this set cannot be closed under whatever type of metric you put. And in fact, set of Minkowski sum of segments or Zonoids, it's not closed in the set of convex bodies with respect to the Hausdorff metric. Simplest example, imagine that you pick these segments, a lot of them centered maybe at the unit sphere, and you just distribute these segments with the top of the segment quite well distributed on the sphere. You take 1 over n, some of these, more or less clear that this converges to a ball. Okay, it's going to be a convex body. In some sense, it has a lot of symmetries, and when you send n to infinity, you leave the set of segments, the sum of segments, set of zonotops, and you approach the unit ball. Okay, and in fact, a unit ball is a zonoid, and zonoids are precisely the closure of the set of zonotops with respect to this metric. Okay, so these are zonoids. I denote zonoids by Z of V. Okay, so before I move forward, I wanted to say maybe a little bit about these objects, the zonoids, because they sound sort of, again, first time to me they sound exotic, but they are very, very popular in functional analysis. For instance, let me give you a characterization of zonoids. You give me a convex body, and then once you give a convex body, you can centrally symmetric body, you can use it to define a norm on its span. So for instance, suppose that you have a top dimensional centrally symmetric body in Rn. You can use this convex body to turn your vector space into a normed space, a Banach space. So question, when is it that this space is isometric to a subspace of L1? Precisely when K is a convex body, is a zonoid. Okay. So the zonoid problem, it is this classical question in convex geometry. It is, I give you a convex body, decide if it is a zonoid. It's pretty clear from this description that this is a hard problem. If I give you a convex body, check that the induced normed structure on Rn turns Rn into an isometric subspace of L1, it's hard, clearly hard. And maybe just to give a feeling of how hard this is, there is a very nice example constructed by Weil. It's a convex body with the property that for every point of this convex body, there is a neighborhood of this point, such that in this neighborhood, it is a zonoid, but globally, it's not a zonoid. So the property of being a zonoid, it's not a local property, okay? It's very difficult to test this property. And in fact, even from this question, you kind of see that it's very much not a finite property, being a zonoid, because you need to check whether it's a subspace of some infinite dimensional space. It's very complicated. But maybe
sorry, one question, Antonio.
Yes.
So would the problem become easier if the convex body is semi-definite representable?
Yeah, that's a good question. And let me answer maybe partly this question in some sense, okay? So I was asked at some point whether the problem becomes easier if the convex body is semi-algebraic, okay? What do you mean by semi-algebraic? Let's say that the support function of this body is semi-algebraic, or even that it's a semi-algebraic set. Okay, question, can you decide whether a semi-algebraic body is a zonoid? And even that, it's still difficult, but surprisingly, I'll just say this, but for people who are maybe familiar with model theory, so if you start with a semi-algebraic body, there is an extension, a minimal extension of the set of semi-algebraic sets, such that the condition of being a zonoid becomes definable in that minimal extension. So for instance, the minimal extension in which this is true is the so-called globally subanalytic set and the graph of the exponential function, what is called R and exp. In this minimal extension, the condition of being a zonoids become definable, which I think it's quite remarkable. And it doesn't answer completely your question. I have more details to say about what you specifically asked. Maybe I can say later, okay? So
sorry, I might have something to say about that. This question about semi-algebra. Just remind me after this one. I don't want to interrupt right now.
Okay, thanks. Okay, so let me go back now to the main question. So sort of like interpreting this type of operation in some ring structure. And there was a word that appeared several times, which was this multilinear, okay, which is something that is there in cohomology rings, in rings, in fact. And here is the first theorem which I want to present, which is a quite abstract theorem, which states the following. So pick a multilinear map between vector spaces, okay? So every such multilinear map has a unique extension, and I will explain in a second what I mean by extension, to a Minkowski multilinear map between the spaces of zonoids. What do I mean by extension? So you see, in some sense, you can fit each of these spaces inside the set of convex bodies by associating to a vector V the convex body 0V. Okay, in some sense, there is a way to fit your vector space inside the set of convex bodies. Just consider the corresponding segment. Okay, segment with the tail at 0 and the top at V. And now you can, if there is such a extension to convex body, to zonoids, so to a special class of convex bodies, I call it an extension if, when you test this extension, to segments of this type, it is the same as applying the original multilinear map to the vectors and taking the corresponding segment. I hope this is clear what I mean. So every multilinear map within vector spaces extends in a unique way to a Minkowski multilinear map between the corresponding cones of convex of zonoids. For instance, mixed volume from convex geometry is the multilinear extension of determinant. So if you take the function determinant from Rn times Rn to the reals, okay, so it's a multilinear map, its unique Minkowski multilinear extension to zonoids is the mixed volume. Okay, meaning that, of course, on the right hand side, I would get a zonoid, okay, and I get a segment of length mixed volume of the original bodies. Okay, so there is in fact a whole class of operations on convex bodies similar to mixed volumes, which come from just picking multilinear map and consider this Minkowski multilinear extension. So let me now use this idea to turn the set of zonoids into a ring, okay? And the construction is very much similar to the way we construct, in some sense, differential forms. In fact, it's very much inspired. So I take zonoids in, maybe, sorry, one question. Let me scroll back. I didn't say, do you know what mixed volume is? So mixed volume is a map from the set of convex bodies in a vector space of dimension n times the set of convex bodies in a vector space of dimension n. So I take n many factors to the reals, okay? And what is this map? Okay, I have to define what is mixed volume of convex body, say A1, AN, and this is by definition. First, you compute the volume of T1, A1 plus Tn, AN, which you can do as a function of T. T are just positive real numbers. Here I'm taking Minkowski sum and then volume. And then this turns out to be a polynomial in the T1 Tn, and the coefficient of T1 times Tn divided by n factorial is the mixed volume. So this is the derivative dt1 dtn at t equals 0. Okay, this is called mixed volume. It is the same formally thing that you do when you do polarization of multi-homogeneous form, okay, of homogeneous form. You turn it into a multilinear map by using this thing, except that here we are using Minkowski sum to do it, okay, but formally it's the same operation. Okay, so let's go back to this. So I take the set of zonoids in V, and now if I want to turn this or something like this into a ring, it must be a group, first of all. And this, as I said, it's a cone, so you can take some of two convex bodies, but actually you can take also formal differences of them. So you can form what it's called the Grothendieck group, which just formal differences, and this injects into formal differences because in the set of convex bodies, cancellation law holds. And once you are taking formal differences, this become a group, at least. And these formal differences, if you pass to support function, for whoever knows what they are, it's just taking differences of support functions. So this thing here, it is the linear span of the support functions of the convex body, of the zonoids. And now I construct first for now, it is just another ring, another group, sorry. I take the direct sum for k from 0 to the dimension of V of the zonoids in the kth exterior algebra of V. So this is like, these are formal differences of zonoids in the kth exterior algebra of V, and I take the sum of all of this. Sounds very similar to what you do when you construct alternating form of differential forms. And the theorem, very simple. In fact, once you have this other theorem available, consider now on these spaces, on the direct sum of these spaces, the wedge product. It's a multilinear map, and this turns this object into a ring. So this multilinear map is used to construct this ring structure on this object. In fact, quite interesting, this ring is commutative now in this case, even if the wedge operation, it is not commutative, but the ring turns out to be commutative. And essentially, it is also graded because the grading is given by the exterior algebra in which the convex body, the zonoid, lives, and the operation clearly it's built in such a way that if you take a convex body in the A1 exterior algebra and the convex body in the A2 exterior algebra, their product, which I denoted by this wedge again, it is a convex body in the A1 plus A2 exterior algebra. Okay, so now just a couple of remarks about this construction, which seems quite abstract. Well, first remark, it is that the set of formal differences of segments in R, it is essentially R itself, because segment, it is decided by, okay, here it's where I should have been a little bit more precise. Here, I mean centrally symmetric. Otherwise, there is an extra R factor. So a centrally symmetric segment, it is just given by essentially in R, you can determine it by its length, okay, which is a positive number. And now, how do you get formal differences of centrally symmetric segments? You get precisely the difference of two positive numbers, which is just the real numbers. In particular, which is what is interesting for me, it is that in this ring, if you pick a convex body Ki in the Ci exterior algebra, and if the sum of the Ci is n, same as this ambient space, the product of these convex bodies live in this thing, okay, which I identify with the real number. So it is a real number, okay? It's a segment which has a length, which can also be negative because we are taking formal differences, and this length is used to identify this product with the real number. That's the same thing that you do when you identify the top cohomology of a manifold, which is maybe, say, orientable and connected with R, okay? It's not exactly R. You need to identify it with the choice of some, maybe, a volume form, okay, which you integrate on the manifold. And moreover, if each of this body belongs to Rn, so not on the exterior power, you take n many of them, you take the product, you get back the old mixed volume. So you get a segment of length, the mixed volume of these objects. Okay, so now let me state sort of a general theorem, which I want to use later to interpret what I said at the very beginning. So interpret those operations which I proposed at the very beginning, so sort of this intersection theory operation in this language, so as formulated in some ring. So I pick M, which is a compact homogeneous space. In fact, I would even prefer, sorry, quotient of compactly group, okay? Compactly group and closed subgroup. I take the quotient. And V is the quotient of the Lie algebra of this by the Lie algebra of the group. So the tangent space to the homogeneous space. Now here is my claim. So first of all, before I proceed, in this homogeneous space, I have a way to put submanifolds in general position. Okay, so you can act with the group action on a submanifold, okay, and you essentially move the submanifold around your homogeneous space. Now, claim. If the submanifold is nice, and maybe I'll say a little bit more about this nice, okay, and it has codimension C, I can associate to this submanifold a zonoid, which I denote KZ, in this Cth exterior algebra of V. Okay, so it's like sort of associating to a submanifold its Poincaré dual, which would be a form. Okay, in the Cth exterior, it would be a C form. But here I associate a zonoid in the Cth exterior algebra with this property that if I pick submanifold Z1, Z nu with the sum of the codimensions being equal to the dimension of the manifold, then when I write expectation here, but really means integration over the group, and I move this submanifold with the group action, this is precisely the product in this ring. So intersection, averaging intersection theory, which by the way, it has a name in this business, it's called kinematic geometry. Okay, I just like a little bit this notation, it's quite fancy. So kinematic geometry, it is actually, it corresponds to a ring operation on the corresponding convex bodies. So in some sense, you can sort of form what in a suggestive way can be called sort of a probabilistic intersection ring, which is a ring in which the nice submanifolds embed with the property that if you try to do this sort of like averaging average intersection theory, it corresponds to doing computation in this ring. By the way, needless to say, in complex projective space, complex submanifolds are nice. You can associate these bodies, and this gives a way to embed the cohomology ring of complex projective spaces inside this zonoid algebra. Okay, so it's a sort of a very large ring in which, in particular, you can rediscover classical complex intersection theory.
So if this dimension, if it's in the higher, I guess,
so
lower codimension case, do you get something about the color characteristics?
Yes. So I just put it here, a theorem which could be a little bit more suggestive. But if instead of having the expected codimension, which is not top, so expected dimension, which is 0, this operation here on the right now correspond to some more sophisticated property, which is somehow not clear how to interpret. But for instance, Shogata, if you want to compute curvature measures of this manifold, okay, Z1 intersected Z0, and suppose this is by itself, it's not of dimension 0, it's some C dimensional, not C is a bad name, it's M dimensional. So you get the corresponding bodies. This object now, it is in the mth exterior algebra, but you can saturate with maybe a ball to some power, the power that you need, which is n minus m, and this gives back some curvature measure. Okay, one has to be careful whether wedging with a ball or wedging with wedge of balls, which is not the same thing. Okay, so a ball in what is needed, it's not the same as the wedge of balls. Okay? It's a different story, and that's why you get curvature measures, because it depends on the type of things you put here, a ball or other things. But of course, there are other geometric operations which yet I don't know how to interpret. I think would be very nice. So to wedge it maybe with some other convex bodies. What does it mean? Does it have an interpretation in terms of some averaging some geometric property? So this I don't know. But I'll give you maybe 2 examples which are interesting. First, I want to explain, if I scroll back a little bit, this example. Okay, this Schubens-Meil example. So if now the manifold is Rpn, and I take, so I said I can associate a convex body to a nice subset, but actually you can even associate a convex body to a measurable family of subsets. Okay, so in some sense, if you have a random hypersurface, you can think of it as a family, okay, of hypersurface of subsets. Okay, it's a measurable family, so it comes with some, it's a random variable with values in the set of hypersurfaces. You can still associate a convex body. It's the same procedure by just a slight, very tiny modification. And the convex body associated to a random hypersurface of degree d, it is degree to the 1/2 times the ball. And now it's the Schubens-Meil theorem. It's very simple. So this expectation, it is the product in our ring. So degree to the 1/2 times the ball, wedge, degree to the n degree to 1/2 times the ball. Now we use the ring structure. So these d to the 1/2, they all go out. I collect them together. Is a product of degrees to the 1/2 times the wedge of all these balls. And now one can do another computation. Of course, one needs to develop some calculus in this Zonoid ring. And the wedge of balls, it is just the unit interval. So in particular, if you remember that I was identifying oriented segments with the real numbers, maybe I should just remove this unity interval and write it this way. Here is another example, which I like. So if the manifold is the Grassmannian of the real Grassmannian, and I take a Schubert variety, so for instance, a variety which is defined by some incidence condition with some subspace, these varieties are labeled by Young diagrams. So to each such Young diagram, it corresponds a zonoid, for what I just said. And the computations in this ring, so the ring generated by this family of zonoids, it is what in a previous work with Bürgisser we called probabilistic Schubert calculus, and it is precisely what one does in this example here. Where is it? Here, this example here. So this volume of K, now you can interpret it is essentially I'm taking the Grassmannian of lines eating a fixed line. That's so the sub-variety, that's a variety. I'm associating to it a convex body, I call it this way. And now by the theorem I just said, the expectation of the number of point of intersections, it is just this convex body wedged with itself 4 times, which is precisely the definition of volume. So it's the volume of this convex body. Okay, so let me conclude maybe with a couple of remarks, which are quite interesting. So going back to complex algebraic geometry. So in complex algebraic geometry, generic and random, so these type of intersections I'm doing, if I am on a complex manifold and I'm taking complex submanifolds, I can take away this expectation. It's just the generic intersection. And this is quite interesting because this establishes a bridge between convex geometry, for instance, and the representation theory. Because you can set up this probabilistic Schubert calculus over the complex numbers. So now you would have a complex analog of this, which is a convex body still. And now you have classical Schubert calculus gives identities between, if you want, how to multiply Young diagrams between them, which is they correspond by some classical algebraic geometry to some essentially operations in the representation theory. But now these operations in representation theory, they have an analog in this ring, this ring of convex bodies. So for instance, I would be very interested in understanding if there is a convex geometry proof of Piery rule. So you just take a tensor product of irreducible representations, you decompose it as the sum of reducible summands, and the coefficients of these summands come out from the so-called Piery rule. Now you can work this thing interpreting, describing irreducible representations as associated to some Young diagrams. You can interpret these computations as computations in the cohomology ring of some Grassmannian, a complex Grassmannian, and at the same time as computations in this ring, in the ring of these convex bodies. So some identities in classical algebraic geometry, they would correspond to identities in convex geometry, which I don't know yet to discover. So as a guiding philosophy I have in mind, I would like to see at some point if there is something analog to the connection between Alexandrov-Fenkel and Hodge index theorem. So it's a classical theorem by Khovansky that Alexandrov-Fenkel inequalities in convex geometry, they are equivalent to Hodge index theorem, which is a theorem about a signature, so the fact that some intersection product, intersection form is hyperbolic. There are two equivalent statements which are connected through what is called the Bernstein-Khovansky-Kushnirenko theorem, which explains how to do computations in the cohomology ring of a toric variety. Okay, there is some beautiful theory, and I sort of like think, and I would just maybe I'm sort of dreaming that there is more of these identities coming from this observation. And maybe finally, I just want to finish with a last concluding remark that more or less everything I said so far also as an analog over other non-algebraically closed fields on which you can put in some meaningful way a measure. And the classical example, it would be clearly the set of p-adic numbers. On the set of p-adic numbers, more or less all these questions that I asked about intersecting, submanifold and stuff makes sense. And with Avi Kulkarni, we did some progress about this kinematic formula over the p-adics. And we have some results. And we are also having some new work with Bürgisser and Kulkarni, precisely extending this type of things over the p-adics. It's still work in progress, but it's an interesting direction that I wanted to mention. Okay, so that's all. Thanks for your attention.
All right, thank you. Let's thank Antonio for this fantastic talk. We have a few minutes for questions. So I guess Professor Bosu has a few questions.
No. Why did you say that I have a few questions?
So I guess you had a few remarks about the semi-algebraic Zonoid problem.
Yeah. Maybe that's can be taken offline.
Okay.
Yeah, let's discuss it. I mean, Antonio, can you show that question about the limit of semi-algebraic Zonoid?
This question.
Yeah. So
decide whether a given semi-algebraic convex body is a zonoid.
Yeah. So you are saying that essentially it's equivalent to given
a semi-algebraic family of convex bodies, asking whether in this family the set of zonoids is a semi-algebraic subset.
So
and
of limits in this zonoid.
Sorry.
So what do you mean by the set of zonoids in this family?
Okay, so suppose you have a semi-algebraic family of convex bodies, which means precisely what you have in mind. So
Yeah.
there is a semi-algebraic set. Okay.
Hmm.
Now, when I say a family, it means that this has some parameter space for this family semi-algebraic set. And now you ask for each values of this parameter, for which values of this parameter you get a zonoid. And the question is whether the set of parameters for which this convex body is a zonoid is semi-algebraic. And deciding whether a given, now a single semi-algebraic convex body is a zonoid, it can be rephrased precisely into the question I put here, is equivalent question. And what we've proved with Leo, my student, it is that in a semi-algebraic family of convex bodies, the set of parameters for this family for which you get a zonoid, we don't know if it is semi-algebraic, but we know it is definable in R annex.
So the reason why I was asking this question was because there was this AMS meeting at Purdue, and there was a model theory special session, and Sergei Starchenko explained something, his work with Peter Zill, and this was that if you have a semi-algebraic subset of Rn, in fact, semi-algebraic family Rn, and you quotient by the lattice. So then, of course, in the torus Rn mod Zn, this thing can be very bad, need not be semi-algebraic anymore. But the Hausdorff limits of the quotient are semi-algebraic. So, and that's not clear at all. I mean, that's, I think, a strong result.
So the Hausdorff limits of the quotients.
So, so forget a sequence. Take one semi-algebraic set in Rn. Let's say a curve in R2. And then take the image of this curve under the quotient to the inverse. This thing need not be semi-algebraic anymore. It can have infinite connected components, but its closure, Hausdorff under is semi-algebraic.
The Hausdorff closure of this set is semi-algebraic. Okay, so that's I vaguely I have some intuition on why you pointed this out in this framework, and I need to think about this connection. Yes, I see what you're saying. So here the main issue is that when you integrate.
No, I understand why this is difficult.
It's a problem about integration theory, but so maybe for the audience, if you take a derivative of a semi-algebraic function, that's clearly semi-algebraic. But if you integrate a semi-algebraic function, depending on some parameter, that's no longer semi-algebraic. Okay, but it is not bad. It is still definable in some minimal expansion of the reals, and essentially testing whether convex body is a zonoid requires doing some sort of like integral transforms, which involve integrations on the of the support functions, and this in the end allows I'm just reducing everything to the bone to decide whether it's a zonoid by in another minimal expansion. But I see what you're saying, Shogata. Yes.
Okay, so that was my.
Any other question? All right, if not, I would like to thank the speaker again for accepting our invitation, and thank you all. Thank you for attending our session. We will meet again next Thursday with the next speaker from University of Wisconsin. Thank you very much and have a good evening.
Bye.
Okay.
Who's the next speaker, Ali, by the way?
It's host Rodriguez from Wisconsin.
All right. Bye.
Have a good day. Bye.
Bye.
Bye, Andre. Bye.
Thank you, Professor.